see the my computer screen, you can see hopefully. Okay.
Yes. Yes.
Okay. So I start my class. So now time is 7:37. Okay. So maybe I'll take a few, not maybe entire 60 minutes. I'll finish by 8:15, I think. Let us see how far I can reach. Yeah. So that correlation measures, we talk about the Pearson correlation measures. So you have to compute the covariance, and covariance is like you have to subtract the mean of individual values, and then you have to do for the both the attributes, so X and Y. Okay. So this is something we are computing the covariance, and then we normalize by the standard deviation. Okay. And we stop at this point here with this figure. Okay. As we say here in this example, that is the correlation is highly correlated and correlation is 1. And these correlation basically indicate the linear relation. Okay. So there is no non-linear relations using Pearson correlation we cannot find. Here what we can observe, that is, this is the so-called x-axis and this is so-called y-axis. Why I am using so-called, ideally this axis is called the horizontal axis and this axis is called the vertical axis. See, it will be nothing wrong if I say this axis is x and this axis is y. Okay, you are perfectly fine. So therefore, but no mean generally what we say is this side is x and this side is y. Okay. So therefore, what we say is more general form is this is something called horizontal axis and this is vertical axis. And generally, but not necessarily, horizontal axis we represent by x and other one by y. Okay. So this is for the terminology. You can you should know it. Now what is we see, whenever the value of x is increasing, as you can see, value of x increasing and value of y increasing. Okay. Here also you can say this value is x is increasing, y is increasing. This value also you can see up to this one. So what you observably you see here up to 0.5, whenever value of x is increasing, value of y is also increasing. Okay, this set of this data, they are basically positively correlated to two set of data. Okay, so these data are positively correlated. But if you see on this one, this is negatively correlated. That means if the value of x is increased, value of y will decrease, or vice versa. Let's say you have a value x and your value of y is somewhere here. Now increase the value to somewhere here in this range. Now what you see is value of y decreases. Okay, and this is quite consistent. Okay, so therefore this is something called negatively correlated, and this negative correlation is the highest. Okay, if you see here and if you see here. Okay, so that is in the last class I wanted to convey it. Okay, hopefully it is clear that what does it mean by negative correlation and other one is the positive correlation. Okay. Here is one example, that is the drawback of correlation. So the value of x is mean. So this is like y equal to x square. What will happen? Value of x is increasing, and here also value of y is increasing here. Here what we see is value of x is increasing, but value of y is decreasing. So this is not very consistent. Okay, so we cannot say this relation is actually linear relation, and therefore we have to have some nonlinear relation. So what essentially what we are trying to do, that linear relation we are trying to represent through a linear relation, that is the correlation or Pearson correlation. So that is, and ultimately we find the value of correlation is 0. As you see, we cannot very clearly see whenever value of x is increasing, value of y is also increasing. So this part is true, but not this part. Okay. So this is the drawback for some applications. If the relation is itself is say not correlated, linearly correlated, so we cannot apply the Pearson correlation. Now, comparison of proximity measures. Okay, so similarity measures tend to be specific to the type of the attributes and data. Someone in the last class, I forgot who asked actually. I think Somia. So that which value you should take, okay, or which measure you should take, okay. So that is really difficult to answer. It based on the particular specific applications, okay. And then what we generally consider is symmetry, or as we learned that few slides before in the last class that similarity value will have some properties, that is it should be maximum is 1 and it should be the symmetric, and some similarity metrics also follow the what is called triangle inequality, but not necessary, okay. So generally we see some many applications the similarity value is symmetric, but as I said, it is need not be the what is called is true always. As I said in the last example, so when you have a 1, that is really true, but whenever you 0, we cannot conclude anything, okay. And many applications, even in recommender system, 0 means actually with unknown. So in that case, we cannot have a very what is called a relation in case of the similarity measures, okay. So mostly the summary of this slide is like whenever we apply particular similarity metric, similarity measures, so it depends on mostly in applications, which application we are going to do or we're going to apply in particular similarity measure. Even you can have your own similarity measures satisfying some objectives, okay. So as I said, when we know that only purchasing is having value, not purchasing item should not giving any weightage. So based on that, we can develop our own similarity measures, okay. But before that, we should know actually what exists. Maybe existing similarity measure might work much better than what you are thinking. Okay, so that is why people should have the literature survey for jumping before jumping any one of the work. Okay, it may happen that whatever you are thinking that already published, say 20 years before. Okay, but you won't get credit for that. Okay, that is why actually you need to have the exhaustive literature. What people did it. It is not only that it will enrich you. Whatever the knowledge it is there, you should know it. Okay, so maybe I spend too much time on this slide. Some of the things not necessary, at least for the BTech students. Okay. So there is a measure, it's called the entropy. Okay. So it is basically the information based measures. So some of the students must do one subject that is called information and theory something ITC. Okay, information and theory coding or something, I forgot. Okay, so information technology coding or something. Coding theory, something called is the coding theory. Okay, so there is actually these type are the things are discussed in elaborately, but nevertheless we'll talk here also. So information relates to the possible outcome of the event. Okay, so transmission of a message, flip of a coin, or measurement of a piece of data, and whether you may have idea whether this item belongs to in which class. Okay, these are the probability that it may be in class A or B. So these are the outcome of the event. Okay, so in this example, we generally compute the entropy. Is a common measures for many applications. Here also we can do. Okay, what is that entropy? let's say we have a variable x and we have the n possible outcome. What does it mean? Let's say attribute. So in which context we are talking about? The context is that we are trying to find the similarity between object X and another object Y. Okay, so that is the context, right? So here variable X is nothing but an attribute. Okay, so it has n possible outcome. What does it mean? That means the attribute X has n different values. In earlier example, actually, is it getting recorded?
Yes, sir.
Yeah.
Yes, sir.
Okay. So we need to compute over a single attribute also. Okay. First, we try to understand what is it, and then we'll go for the finding similarity between a pair of attributes. Okay. So as I said, the here outcome is nothing but n different values. So let's say eye color. Okay, eye color can be, if it is a human, it may be two types. One is the gray color, another is black. Okay, so therefore there will be two outcomes. Okay, so let's say for generalization we have n possible outcome, and each is having some probability. Okay, so with probability P1, P2, and Pn. So therefore, what we can do it, entropy of a single variable can be computed summation over number of outcome, and then what is this term? Pi log Pi. Okay, so don't ask me how this formula comes. So you just consider this formula is right. Okay, that will be a different subjects for how the formula comes here. Okay, so therefore Pi log Pi. So Pi is what? That is the probability of the outcome I. Okay, and then you do the sum of for the all outcome. So that is the formula for the entropy. So what will be the maximum value? So this is the probability, means summation of this all probability will be 1. So let's say P1 is the probability 1. So rest of the value will be 0. As you know that log 1 is 0. So therefore entropy minimum value will be 0. Okay. And what will be the maximum value? Maximum value when the probability of each outcome is equal. Okay. So in that case, we'll get the maximum value is log n, because we'll have the term n, and then what is 1 by n into log 1 by n. So we'll get the value of log n. Okay. Because if there is a 3, so probability of each will be 1 by n and log 1 by n. So we'll get the maximum value will be log n. Okay. This formula will be used in maybe after 3-4 class to compute the what is called Gini index. Okay, impurity, not in Gini, to compute the impurity of a particular node of a decision tree. This formula, same formula will be used. Okay. So this is one example that how to compute. You have a two outcome. So one is 0.5, another is 0.5. So this is the formula for computing the entropy. So what is the entropy of the fair four-sided die? So four-sided die means it has 4 outcome, and that is fair means each will have equal probability is 0.25, and then you compute it here. So that you will get the entropy. This is one example. So for outcome, there are 1, 2, 3, 4, 5 outcome. Okay. So what will be the maximum value? Maximum value will be log n. Okay. So log 5. Okay. Yeah, this is more elaborate. I think you have must have understood by this time. That is the how to compute here is like instead of probability Pi, how do you compute it? So we have the n different values. and we have total number of observation is m, and mi is a one distinct value, and we have n distinct value. So therefore, probability how do we compute it? Mi by m, and this is the same thing, pi into log pi. Okay, so this is the probability also. This part is also probability. Okay, and we have to do for n times because we have the n distinct values. Okay, so that is it said key how to compute the entropy of an attribute, but it is difficult for continuous data, so we have to make bins and then we have to compute. Okay, now we come to the similarity between two attributes. So this is one way to compute the similarity between two attributes. So let's say we have two attributes, one is x, another is y. This is something called mutual information. Okay, so how it is computed? It is a function of individual attribute and join. It is individual entropy and join entropy. So is it a connection issue? I don't think it's fine. Okay. So now what is that formula? I am putting the formula directly, that individual entropy that few minutes before we described, and then you subtract the join entropy. What is the join entropy? So join entropy is, let's say we have an object x, another object y, and now the obviously x is object and x is an object and it has different distinct value. Object in a sense, I am maybe wrong. It is not object, it is an attribute. Like attribute will have a value and y also will have a value. Okay. So now what you do it, we'll see the Pij. What is Pij? That is the distinct value from x and distinct value from y occur how many times, and you take the probability. So here what we do it in earlier formula, we have only a single value. Let's say eye color. There are 4 different types of eye color here. Okay. So then what is the value of h? So then what you do it, you take the summation over 5 and then you take this value. Okay. But now here is like join entropy. So join entropy means actually join that two values, that two distinct values jointly, how many times it is occurring out of the total number of samples. Okay, so that is Pij. Okay, so what is the maximum value of the mutual information? It is like minimum of nx in y. Nx in y is nothing but the number of distinct values. Okay, either from x or y. Okay. So I think this will be very clear with one example. As in the last class, ironically, I said key many times, we are very happy to learn from example. So let us use that tricks. Okay. So we have two attributes. One is student status. So it will have two different values. One is undergraduate and another is graduate student. And then another is the grade. Okay, this is another attribute. So it has 3 values, that is A, B, C. Okay, and this is the statistics for 100 students. 45 students belongs to undergraduate and 55 for graduate and so on. And 35 is A, 50 is B, and then C is only 15 guys. Okay, and then we can compute from here is what is called is entropy. Okay, we have computed here and then you add it and then you will get the entropy. Similarly, we'll get the entropy for grade. And now what you have to do, you have to compute the joint entropy. How do you do it? So if you see the formula, we have the summation, double summation. One is summation over I. What is I? I is the distinct value of attribute X. Y is the distinct value of the attribute Y. Okay. So then what do you have to do it? You have to combine undergraduate to A. And how many student undergraduate is A? Undergraduate and got grade A, count is 5. Okay. Undergraduate, but student number of student grade B is 30. Okay. Similarly, undergraduate and student grade C is how many students? So 10. Okay. Now again you combine with the value graduate with A, graduate with B, graduate with C. So then we'll get the joint what is called joint probability. Okay, so undergraduate A count 5, we got it, and this probability is 0.5, and then we can compute it here. So now in the previous slide, we have a summation over ij. Now we got Pij. What is Pij? Pij is nothing but for undergraduate A, this combination will get the value here and then log this value. Similarly, this one will get it, this one will get it, and so on. And then what is the HXY? That is joint entropy. Joint entropy is nothing but this value. Now, what is that? Mutual information of the student status and the graduate. So what is the mutual information? Individual entropy subtracted the joint probability, joint entropy. So that will give you the value. Now, question is, can the mutual information be negative? So what is the minimum value? That is log minimum of nx ny. So this cannot be lesser than 0. Okay. The question is, can it be negative? So you check out. So as I said, it is really difficult for continuous attribute. Okay. You have to make different bin, and then you have to see the values, and then you have to go with. Okay. So this is the way for the what is called is for the continuous attributes. Okay. Now the general approach for combining similarities. Okay. So now we have studied many similarity measures, right? We have used the mutual information. We have used Jaccard. We have used cosine similarity. We have used we learned the Pearson correlation. Okay. And there are many other correlation also. Okay. And then if anything we miss it, okay, then SMC. Okay. Now what happens is, suppose one object is described with a set of attributes, as I said in the beginning of this class. So therefore, one attribute might be ordinal, another attribute may be numeric, another attribute something else. Okay. Now what do you want? We want a single value, not a vector. Single value for computing similarity between a pair of objects. Okay, and then this pair of object has this pair of objects have the what is called is what I wanted to say ki we have a set of attributes for each of the objects. Okay, and then we want to compute the similarity between these two objects. Okay. So in that case, what we can do it, some of the objects ranges from 0 to 1, some other thing it will range. So then what you have to do, we have to combine this each similarity values. Okay. So therefore, whether it is a symmetric or asymmetric, if it is asymmetric, we put 0, so we will not consider. Only if it is a symmetric, let's say we consider or not. So this is one way to, I won't say this is a perfect way for doing. This is one way for computing the similarity between a pair of objects. So SKXY. So here is the similarity. You can use Jaccard, you can use SMC, you can use the cosine, you can use the Pearson correlation or other measures. Okay. So this is a very naive way for measuring the similarity between a pair of objects. Now another way is like, as I said, you give more weightage for particular attributes and you give less weight for the other attributes. Okay. So in that case, that weight factor will come, and this is an indicator whether it is symmetric or non-symmetric. This will be one, whether you want to give important or not. Okay. And this is the weight factor. Now question, how do you set the weight? Again, the question is, it is very difficult to, the answer is very difficult to tell how do you set the weights. So what you need to do it, you have to get information from the domain, or otherwise you have to get information from the, there is something called validation set data, validation data. From that validation data we get it. Okay. Another way to find the distance measure is like while computing the distance measures for, let's say, Euclidean distance, Minkowski's distance, we use this formula. But unfortunately or fortunately, this WK was not there. What is WK? WK is the same way here. WK is the weight we are giving to particular attributes. Okay. Let's say some attributes. So let's say when we compare between two students, okay, whether how close the two students are, very often we compare the grade between these two students. Okay, so there may be another different other aspect, other curriculum activities between them, but we don't consider much. Okay, one way we might be wrong, but how do we do it? We give more emphasis on the how much grade you got it. Okay, so therefore that corresponding grade. So it is an ordinal attribute. While computing the distance, what we can do it, we can give weight, some weighted very close to 1. And for other attributes, we can give the weighted very close to 0. Okay. So that summary of this last two slide is that, so we compute the similarity, but some application, it is not necessary that you will have the all attributes numeric. Some of the attributes will be ordinal, or some of the attribute will be cardinal, categorical attribute. So in that case, to tackle this one, we need to compute the similarity individually, and then we have to combine them. And how do we combine? Okay, so that is the summary of the last two slides. Okay. Now some of the thing is like the density. In some application, we don't consider the so-called the Euclidean distance, or whatever the measures we have considered. Not directly we use them. Okay, so one is that we measure the density. Obviously, while computing density, we measure a kind of distance measures, but not a, say, let's say Pearson measures or something like that. Okay, so density in physics, you have studied that density is nothing but mass per volume, right? D equal to m by v. Okay, so in our context here, formula almost remains same. Okay, but how we interpret the same thing. So here Euclidean density is nothing but number of points per unit volume. Okay, so how points come here? As I said in the beginning of the class, that determining class, I said ki one object consists of a set of attributes, and these objects, once we say this is an object, some other time we can say this is a pattern, some other time we can say this is an entity, and sometime we say this is a point basically. Okay, in d dimension, if there are d attributes. Okay, so therefore we say that an object is nothing but it is a point in Euclidean space, or it is a point in d-dimensional Euclidean space if it has d features or d attributes. So that is why now question is, when we consider the what is the density of a point, that means what is the density of an object. That object is represented as a point. Let's say it has two features, height, say human being. So it has two features we consider, that is height and weight. Now that each human being can be represented as a point in two-dimensional Euclidean space. Okay. Now if we want to find the density of a particular point, that means density of a human being. What do you do it? We find the number of points per unit volumes. The points which locates nearby, we should have a volume, and then we see the how many number of points within the periphery. Okay, so that is something called Euclidean density. So other approach is like we estimate what is that, say we have a set of objects and we plot it, and then we'll see is the which distribution does it follow. Okay, so that you will be elaborately learning in machine learning classes, that how to estimate the what is called is distribution of a data set. Okay, I am sure that you will be learning this, and Anup is teaching, and surely Anup and Ratnakar sir both will teach this part very nicely. So that is one way. Another is graph-based approach. Okay. So this is beginning of this class. This density concept is heavily used in case of clustering and outlier detection. That will be used, we'll be telling about in details later on also. So this is one approach. Let's say what you do it, how to find the density, what you do it, we have a set of points. What you do it, we divide the x-axis or horizontal axis into a number of what is called interval. Similarly, we divide the points into y-axis also number of interval. So we'll get a cell. This is something called a square. Okay. Now it might be a rectangle also. Now same thing it happened. This is for 2 dimension. If it is a 3 dimension data, then obviously we will not say this is a rectangle. We will say is the cube. Okay. If the length is same, otherwise you will say is the hyper rectangle if it is more than 2 dimension. Okay. So now what do you do it? So let's say I want to find what is the density in this region. So what do you do it? We'll start counting how many points. As I said few minutes before elaborately, that here point basically indicates an object. So how many points are there in this rectangular or cube or rectangular or cube, what is called in square? So that will give you the number of points, and we consider this is unit. So that number of point is per unit volume, means number of point is nothing but the density of this region. Okay. So here is some points, and let's say this is 18 points. So this is 1, 2, 3, 1, 2, 3, and then 18 is here. Here they have counted there are 18 points. So density of this region is the 18. Okay. So there are many ways also we can compute the density, but basic idea is that you have to count number of points in a unit volume. Okay. So instead of cube, what we can do it, we make a square. Sorry, we can make a region. So that is like a circular region. So we can have a density instead of volume. Then we'll get the density in 2D case, and then number of points in per unit area. So that will give you the what is called is or maybe 2D it is area. Maybe if you go 3 dimensional, so you have a cube, and if you go more than that, we will have a hypercube. Okay. One example, another way for computing the density is like in other way I said key. Here is we want to compute the density of this point. What do you do it? We draw a hypersphere of radius r, and then we compute the volume, or we compute for higher dimension, or we compute the area and the number of points divided by the area, or what is called is the what is that number of points per volume? Yeah, for divided by the volume of hypersphere or cube. Okay. So and then many times what it is done is it is considered as the unit volume. So therefore we only consider the number of, say let's say density of this point and density of this point. So what you do it, we count the number of points divided by the volume. Here also we'll have the same number of radius. So then we compute the number of points by divided by the volume. So if you carefully say in both the cases, the numerator, denominator is having the volume. So therefore it is fixed only. So therefore to compare whether this region is more dense than other region, so we only see the numerator part. Okay. So these things will be discussed elaborately also in whenever teaching for clustering, density-based clustering and outlier detection. Okay. So I think this is the last slide for today. Okay. I might have gone little faster way. I'm not sure. Okay. So this is the slide, last slide for today. So if you have any queries, maybe I'll be happy to listen. And then I'll try to address also. And in the next class, we'll talk about some of the things here. Okay. And next class will be on Thursday. Okay. So no class on Tuesday. Next class is on Thursday. And Friday is very likely is a holiday. I don't want to waste holiday, but maybe not maybe I will take that Tuesday's class, that compensatory class I will take on Saturday. Okay. So now if you have any queries, I'll try to address. Mona Lisa?
Yes, sir.
Any doubt?
No, sir. It is understood.
Asin? You are not audible.
Yes, sir.
Any doubt?
No, sir. Clear.
Arijit Mohanty? Arijit? Left? Arijit Mohanty? I think we have very less number of students. Or they left or what? Oh, 75. So quite good number. But I could not see somehow. Okay, see more. I think Joy is there. Aman, Joy is there.
Hello. Yes, sir. It's Jay.
Yeah, Joy. I think you messaged something. I could not recollect what did you message?
Yeah, that day, sir, you had to schedule some compensatory class.
But you
So
missed it.
at that
Okay.
day, I was at the vaccination center. That was the message.
Okay, that is more important.
Sorry, sir.
I think that is more important than this class. You should be vaccinated because institute may call you if you have a two vaccine, both of those of vaccine completed, then only you will be allowed. Okay, I'm not sure.
Yeah, yes, sir.
So I think many of you will be very.
Sir,
you are
Arijit
excited
is
to
having
come
some
back.
microphone issues.
Ashish. Okay. So it is a one-way communication. So you have
Sir,
any doubt? It's okay, fine. You have any doubt?
sir, no doubt. But one question you told about some compensatory class on Saturday. So which Saturday? This Saturday or next Saturday?
Next Saturday.
Next Saturday. Okay.
Next Saturday it will be. Today is 3rd, 10th. It's Friday, right? No, 11th. Okay, 11th Saturday.
Okay. Thank you.
Okay then, huh? So I think class is going fine as far as my end. I don't know from your end. So you need to speak out. Okay. As you know that number of classes is very large, and marks is okay one thing, and but there are some other scenario that this subject as data science is dropped, and maybe to catch the machine learning hype. So this is the only subject that you can obviously you have the core machine learning subject, but this is also parallel to machine learning. I won't tell you this is a machine learning subject. It's no. Okay, it is a data mining subject that is very close to the data science. Okay. So therefore, if you have an issue, you can also have question on chat box. I can see later on. Or directly also you can ask. This is a good time to ask question because no one is seeing you that who is asking question. Obviously, I'll see. They will see it, but actually you are not visible. Now actually, see in many meeting, my experience is, let's say if we have a senior professor, okay, many times we skip the asking any direct question to higher authority, but this is a good time. We don't know actually. So among 70, 100 faculty members who are the senior and other things. So therefore, it is always good to ask questions. So yeah, there is question already. So I think I motivated some of the guys. Yeah. Ramakant, do you have any question? Okay, it seems no. I should not be happy that I motivated some guy. Okay. With that, actually, I think I stop today's class and then we'll meet on 9 o'clock Thursday. Okay. Okay, bye. Good night.
Okay. Good night, sir.
It's a
Good night, sir.
Okay.
Good night, sir.
Good night, sir.